Use a synthetic Argo distribution. So it's a distribution that was created by Gasparini et al. In 2019. And it's based on existing Argo distribution that represent something like 3 to 3 degree. And here we supposed that all these Argo profilers, they were equipped with PCO2 sensors. And we will have 3 data sets, like for 3 different experiments. The first one is based on SOCAT data only. So it's a data that we use the small period, not to use the too heavy data. So it's from 2008 to 2011, and we will try to reconstruct the February, just 1 month, from 2008 to 2011. So the first experience, it's SOCAT data only. The second experience, it will be SOCAT data plus the distribution of Argo profilers, but only 25% of the original proposed Argo distribution. That I repeat, it's 3 to 3 degree distribution. So we use here only 25% of it. And the third experiment will be, again, only SOCAT data, and again, 25% of original synthetic Argo distribution, but only in the Southern Ocean, because it will be quite interesting, the influence of this data, additional data, just in the Southern Hemisphere. And so what's exactly the data we have? So we have this distribution from observations, even if it's like synthetic observations, and all this location of these real observations were colocalized with ocean biogeochemical NemoPSKIS model grid. So now all the data that you have, it's data from this ocean biogeochemical NemoPSKIS model. So this model has 0.25 degree nominal resolution and 5-day time resolution. So we just subsample all these real locations to the model grid. And now we are telling that this model is our truth. And so we will compare the machine learning output with this model. Is it clear? Okay. So let's speak about the features. To test our machine learning here, we need 2 databases. It's our targets and a set of drivers. So the drivers, it's what will be input in our machine learning model, and the targets, it's what we want to reconstruct. So for us, it's PCO2, ocean surface PCO2. So the predictors to reconstruct PCO2, so here there is a list of them, and they represent these physical and biogeochemical drivers that drive PCO2 variability. So it's a sea surface salinity, sea surface temperature, mixed light depth, chlorophyll concentration, sea surface high, and atmospheric CO2 mole fraction. And also, we will use the anomalies of all these variables as additional predictors, as well as geographical coordinates, so it's latitude and longitude. When I repeat again, we just reconstruct 1 month in this exercise, February. So before we go, it's quite important to normalize all our data. So for example, chlorophyll and mixed light depths, they have they call like skewed distribution. So if you plot it, it will be something like this and go and represent a lot of zeros. So we log transformed it. And for the rest, it's also quite important to normalize the data, to center it to zero mean and reduce to unit standard deviation. So why it's important? Is that to put all our predictors in a comparable range and also avoid getting like more weight to some predictors that have larger range variability. And as I said, we will have geographical position also as predictors, and see here there is a following way kind of how you can normalize it. The latitude is quite simple, and longitude because of this periodic behavior. So we will have two drivers, so longitude 1 and 2, it depends on sinus and cosine. So for you, it's already all done. So it's normalized. So you don't need to care about it too much. And yeah, let's go to exercise. I hope everyone succeeds to the import packages. So the first step will be, of course, so we will read and visualize the data what we have before train our feed-forward neural network. So the data they are in CSV format, and we have two data sets. It's data for training and data for evaluation. So this data for evaluation, it's not for validation, it's to evaluate the model in during the training. So it means that in every step, the model will check with evaluation data and to correct its weights. So yeah, if you try to download it now, it will work. So it's quite quick, all good. Yeah, so in within climate, it's quite important to understand what we have and to analyze our data. And this step, so we will visualize our data. So you should have something like this. Training data. And if you run the next one, so this is evaluation data. Also, as explained in the notebook, the evaluation data we take in like each course point. So we have 75 data for training and 25 for evaluation. So what, yeah, we have the question here. What would you conclude about the future output of machine learning based on these three different data set? Which one you think will provide the better accuracy of pt2 reconstruction? So when we look here, and yeah, it's like quite logical. If you have more data, so better accuracy you have. Okay. So now, yeah, let's go to the neural network, and so we will try to train our model, visualize our results, and we'll see if our hypothesis that the second set of data will provide the better results. So here we have our quite simple feed-forward neural network. You can see here. So I just quickly explain here that we have 15 input nodes. So it's all our drivers, so drivers and the anomalies and geographical positions, and yeah, some hidden layer and output. Also, we will use, it's quite useful, the early stopping to avoid overfitting. So if you, in two, there is no really like rules how to build your architecture, what optimizer to choose, what the best activation function will be in your model. how many hidden layer. It's better to, yeah, more hidden layer, it's better, so you have a better accuracy. But it's also like a lot of empirical work behind it. Just there is also what we follow some empirical rule that depends on number of data that you have for training, and it's better yeah, to use like a factor of 10 compared with your data and the number of parameters that we will introduce in our model. So just run this one, so it's just definition, and the next step is to realize our model, and this cell will also print us a number of parameters. So how many parameters do you have? Total number of, sorry? Yeah, the total number of parameters in your model. So everyone succeed to run this cell? So how many parameters do you have, guys? Same number? Yeah. So, yeah, do you think so? We, yeah, I didn't print here. You can find the way, like, for example, the data that we just download. Before, I would say we had something around 12,000 points. So do you think we are we are good with this empirical rule that I mentioned before? Like everybody with the sleep after coffee break. Need to take more coffee. So yeah, it's around like factor of 10. The number of data point we downloaded before, and the number of parameters. And just to be sure that you understand what we're doing, can you find and tell me in how many iterations model will stop if there is no improvement? So this is about early stopping. If you go and to see the structure of our machine learning and the early stopping function, can you find the number of iterations? Everyone, did everyone find it? Yeah. So now let's train the first model, and so this is the first data set there where we have only SOCAT data for February from 2008 to 2011. While we are waiting, yeah, after, if you have time and very curious, so I can advise also you can change a bit the architecture, like maybe add some more hidden layers or remove, or yeah, just to play and to see how you can change the accuracy, also play with the number of the iterations that model can yeah, wait before apply early stopping. Also, you can change, for example, your optimizer here. We use the RMS probe, so you can try different alpha activation function. So the choice for this model, it's, yeah, as I said, it was based on some empirical tests. So my model is done. So yeah, early stopping worked here. So it means that during 30 iterations, model didn't see any improvement and just stopped. And now we will plot loss function. So you see here, so what's happening with the loss function showing us the error. So it's reducing with each iteration. The blue based on training data and the orange on the evaluation data. It's losing. So what do you think? Do we have overfitting or we are good? Yeah, Laura think yes, but so, you agree? Yeah. Okay. So now let's just run to next cells. This will be second and then third data set. And after that, we will plot three figures with a loss function for 3 data set. Also in this notebook, so there is a link for the paper where there is like now like 11 different observation system simulation experiments where we played with a different number of Argo profilers. We also test the case where we have just Argo profiles everywhere. And so this is very important exercises also because yeah, at the end you will have this question, like to choose the best model, because it's not only like to have as much data as we want. So in the model work, we can do it. But when we go in real life and speak about this campaign of deployment, different instruments, so it's quite important here and to understand very well and seriously where this area, where we need to deploy our instruments and how many. So when you work with observation system simulation experiments, you need to find some equilibrium between the accuracy, yeah, between the accuracy and also the realism, what we can achieve, and the cost of these campaigns. I think my second run is done. So just run the third one. So it's also a good example to show what we can do with models. It's not only to work to predict weather and climate and understand physics, but it's just one more tool. So we can have some apply it to make some decisions. Have any questions while we're waiting? Yes, overfitting mostly it means that our model is a good word to use. So close to training data, just like, yeah, mostly like reproduce just only training data. Then you will see that this training loss will continue to reduce and maybe stop somewhere, but the evaluation will go somewhere else. that it's the blue line will reduce in the orange, and the orange one, green. It's too far. Okay, so I can plot now these three loss functions. Did it work for everyone? Yeah. So yeah, it looks quite similar. So by the end, so you see still some oscillations in evaluation graph. So it's normal. And yeah, we go to the next step. That's quite interesting. And now we will analyze our results and to see what our model produce. So it's a validation of the machine learning models. So it's another data set that normally it's a data set that did not participate in training or evaluation. So in this particular case, because of the size of data, that to make it easier to download and so on, yeah, it's not really proper validation data, because this data, they include a whole Atlantic Ocean, including the points that we use for training. But you still can see the accuracy of our models, just to keep in mind. So if you want to do like proper validation, it should be the data that your model never seen before. So we'll download this data, and then this cell will print us the validation loss value for three data sets. When it's already done, you can start to think about this question. So what you can conclude just looking on these numbers. And if you remember, at the beginning we said that the second data set, where we have more data, will provide us better results. Done for someone? Yeah, what do you have like numbers? Okay, so yeah, obviously the two last, they show better accuracy, but what you say like about between these two last? But they're comparable, say, yeah, the two last data set, even like we have like half maybe of Argo profilers, the difference between two of them, we still see that the accuracy is quite comparable. But I always say when we work in weather and climate and with the machine learning, so very often used to represent like one single number, and for accuracy like RMS difference or correlation, some average value. But it's quite important also to see your map, because very often there is error compensation. So you have very good accuracy in some area and very bad in another, and your mean average is amazing. So it's quite important to visualize your maps, and that will be our next step. So we will estimate and visualize the model statistics. It will be RMS. The first we will compare the mean between these 3 February, 3 February from 2011, with the mean PCO2 value from NEMO BSCIS model. We will see the difference of this mean. We will see the RMS error, standard deviation, and correlation. Quite slow. Yeah, and just see that I wrote here the hint. So as at the beginning, I said all our data drivers and also targets, they were normalized. So now when we go back and we want to visualize, we don't want to visualize this normalized PCO2 because can't understand what is it exactly. So we need to apply again the standard deviation and the mean. What we explicitly you need to use the same mean and the standard deviation that was at the beginning. So it already was in the file, and also to economize the time, it's already all written in the notebook. Waiting for my notebook to finish. So if someone still waiting for the accuracy for this step, it's done. You're waiting. I'm not alone. Are you done? Yeah. Okay, just me. Okay, so let's download the data. So you just go through all these cells. So it's okay. Work for you, or you have some? No. Have same lines right here, yeah. Yeah. I needed to finish it. I forgot that this the target data, so I didn't download it. So we just need it. So if you go further, so normally here we go from normalized PSU2 to real value of PSU2. We multiply by STD and we add the mean value back. And so here we calculate the difference between reconstructed data and the data from Nemo Piscis model. It will be different that we will plot further. And we calculate the mean of these values. So the all data, they're in the same data frame. So you have your PSU2 values and the difference with Nemo Piscis model. And if you run this cell, so it will plot you. It will plot the mean value. So the first map, it's the mean PSU2 from Nemo Piscis, and 3 others, it's what was reconstructed for 3 different data sets. So can you see, do you have your figures? Yep. So you now can compare with the first one. So what would you say? No, this is just a mean, because we have the, it's not the difference. So it's like PSU2, average over February from 2008 to 2011. So the first one is our, what we call truth. It's a model data that we compare. So, I cannot see it yet, hopefully soon. Sorry? In reconstruction. So what, for example, the reconstruction with the first data set, yes. So you have the same error. Did you run this cell before? Finished. Now for me, because I stopped it, and actually I need the here. No, because here we open the data that we want to use for validation. Then we apply it to already pre-trained model, so they put in and so here it's create the reconstructed value. So I need this data that I will use again to create the data frame. So if I don't have it, I can't really like show you the correct values. I don't know why it's the last one. It's running so. Then it will be the same.
Yeah, it will be the same. Oh, the Vidale.
But it's good. Of course.
It would just, yeah, just completed it.
Let's try it. Yeah, so you now I have figures like you, and yeah, what's interesting here is when we just see these means, not really, yeah, maybe in the color bar or something, not really, it's not so emphasized as a difference, but already we can see that there is a quite high values in the South Atlantic. So here that is missing when we use just yeah, so here, so this is in our model, and you can see in the first results where we just had SOCAT values, and we didn't have too much data in the southern hemisphere, so it is missing. And also, as someone mentioned, that the value is a bit higher in the North Atlantic. And if you go to two others, we can see that there is already this local maximum that appears, and maybe in the North Atlantic also looks a bit better. And the next cell, this plot us the differences. So what would you say? Which one you would choose? We introduce some Argo profiles. Does it improve? Does it matter if we have this data in the North Atlantic or? Okay, and yes, so here, yeah, let's plot the standard deviation. Show us more about and say more about the variability of pt2 compared with what we have in Nemopiskis model. So the first it's Nemopiskis, and this is 3 our different models. So as we've seen before, yeah, when we have just SOCAT data, we still have this problem in the southern hemisphere, even a bit in the north hemisphere as well. And introduction to the Argo profiles improve quite well our statistics. So the variability, yeah, the standard deviation quite comparable with what we see in Nemopiskis model. So yeah, we still have some areas that need more attention, but we can speak about it a bit later. And yeah, still, if it was up to you to have a decision, compare, yeah, just based on this mean difference and yeah, this standard deviation, what would you advise for deployment of Argo profilers? Sorry? A bit more near Antarctica. Yeah, and the last statistics, it will be the correlation coefficient, and then we can discuss. It's correlation coefficient between NEMO model and our 3 tests.
So I had something, yeah, the idea would be one system, which means the four cells that have temperature, salinity, spaces. We issue cells that we could answer the dilemma. Could be, yeah, but the program itself is really, yeah. So, but what is the relative profit? How do you spend it on more close to the running profit? We like that we mostly have put those in a few digits, but the digits that even if it's so how and be part of it, the digits that yeah, I would have to and we have moved to the top of the yeah, to stop and stop. Finally, the question. Great, I know. That's what you can probably look at it.
Yeah.
different processes that all make that, yeah, I probably really like how it actually gets the process.
Also like idealized case, so because it's like in a model and like you have all these outputs, they're comparable because same grid and so on. But yeah, you're right, probably there is something in the model inside itself, I mean ocean model, yeah. Maybe yeah, if you say here, but here I would care. Yeah. So now, yeah, we have the last one. This is a correlation map. And yeah, when we have just SOCAD data, we introduce Argo profiles everywhere in the Atlantic Ocean and just in the southern hemisphere. So the correlation in the third case quite good, you can see. So yeah, if it's, yeah, what would you say? What you would advise to Argo campaign to do? Because their idea was, yeah, to go in the Atlantic Ocean and to deploy the BioArgo every 3 to 3 degree in all Atlantic Ocean. You don't need it. So if you, yeah, you have like, I know you need to think about your financement and yeah, also be like environmentally friendly. Not to put too many stuff in the ocean, we have already enough. So, so this is experiments is quite good, and also as to do like quite quick and good progress in science and answering different questions. There is a lot of work, for example, in the Southern Ocean to understand different physics from biogeochemistry and just ocean physics and so on, because there is no enough data. So there is a lot of campaigns also to develop this region and to concentrate more attention there. It's also why I think I would say almost all ocean models are struggling with physics in ocean, in the Southern Ocean, because we don't have data. So yeah, the exercises like this, it's quite important, I would say. And also you've seen how it's important to plot and to see exactly regionally, because what we saw from our first results from the first statistic, this accuracy, what we just saw in the number, and we said that the two last data sets where we have Argo floats, they were comparable, but actually when we go like to regional comparison, so we see that yeah, it's comparable, but there is one of them that is better. So where we have less Argo floats. So it's always important to see what is behind these average numbers and to analyze it. Okay, so do you have any questions? Yes. You can play with color bars, but also when we so the color bar is also quite yeah, good question, and there is a lot of discussions. I don't know if you're all aware, but I work with some people who don't remember, they're not really good with coloring, and this color bar, for example, was proposed some kind, yeah, that can help people to see better. So all this cool, warm color bars doesn't work very well now. And when you publish your scientific paper, you need to really think now about it. And how are you doing? No, we tried 25% and 10. And 25, but I think there is a link, so you can go there. I would just try it if you have, I think I had it, yeah. Yes, so like there is this table, so we had like 11 different experience to try. It was if you have all Argo distribution, like 3 to 3 degrees, then we try to reduce to see what, like we go to 25 and to 10, because also I think our aim was to go as less as possible. And as we had a lot of experience in quite short time, like it's very often in science, so you have like short contract, make some choices. Yeah, no, 10 it was not enough, but 25 we found that it was quite, yeah, quite good limitation. Yeah, you can. Yeah. Yes, we found. So this is a description of all this experience. So what's the data we have here, and a different combination of SOCAT with different distribution. Yeah, no. Yeah, so also, like, there is another question when you are doing this, then what we discussed about the ensembles and the error propagation, and this is all, you have your measurements that they also have some errors. So it's interesting. So next step, for example, for this work can be introduce some perturbation in your model data, and to see how machine learning will react if we still have same statistics. So this is like analysis of like measurement biases and like systematic biases. So in the end, you have like list what you learned today, and I hope it will be useful in your work. So I think it's applicable, not just in this case it's quite wild exercise, so you can apply in different domain, I would say. So now you know how to open and visualize some geographical data. So, you can see the list here what you learned. So, and also some very simple pictorial neural network. And I advise you, if you have time and some curiosity, just change some parameters and to see. You also can change the data set, for example. You can, just train, for example, your model on the data only in the North Atlantic and try to see what is happening in the South Atlantic. So it's also very important when you're using machine learning and you're coming from a domain, mathematical, like let's say domain, it's not only about numbers, because it's also how your data is distributed. What I was trying in all my machine learning application, it's always to choose like training data and this evaluation data not far from it, because otherwise it doesn't make any sense if you work with climate data or environmental data. So you need to think about it as well. It's not just numbers, it's physics behind. Yeah, I hope you enjoyed. Maybe people look so very hungry now. Yeah, so and if you have questions, you can contact me. And, thank you.